This is SpaceTime, Series 19, Episode 87, for broadcast on the 7th of December, 2016. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe. You can download SpaceTime as a free twice-weekly podcast just about everywhere, including iTunes, Stitcher, Pocket Casts, Bytes.com, YouTube, SoundCloud, Audio Boom, and from spacetimewithstuartgary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C. Coming up on SpaceTime, more evidence that a supernova led to the birth of our Sun and Solar System, a great rift valley discovered on Mercury, and a Russian Progress cargo ship crashes and burns shortly after launch. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
There's new evidence that the supernova explosion of a star 12 times more massive than the Sun triggered the birth of the Earth and our solar system 4.6 billion years ago. The findings, reported in the journal Nature Communications, are based on a new study of meteorite samples. The new results add to the existing hypothesis that an event, such as shockwaves from a supernova, the explosive death of a massive star, generated the energy needed to disturb and compress a nearby cloud of molecular gas and dust, causing it to collapse gravitationally. As densities inside the collapsing cloud increased, the pressures and temperatures got high enough to trigger multiple instances of nuclear fusion, each forming a protostar surrounded by a protoplanetary disk. One of these protostars turned out to be our Sun, and the surrounding protoplanetary disk ended up forming our solar system, including the Earth. Scientists trying to understand the earliest history of our solar system have focused their attention on a specific type of meteorite known as a carbonaceous chondrite. Carbonaceous chondrites comprise only about 4% of all meteorites observed to fall from space. The best known of these is the Allende meteorite, which is notable for possessing abundant tiny millimetre to centimetre sized light-coloured structures called calcium aluminium-rich inclusions, or CAIs. These fine-grained microscopic structures are probably the oldest substances in our solar system and were among the first solids to condense out of the protoplanetary disk from which our solar system formed. They have strange isotopic signatures that point to interstellar origins, things older than our solar system, and are thought to be the byproducts of a nearby supernova. The Allende meteorite is the largest carbonaceous chondrite ever found on Earth. The fireball was witnessed at 1:05 on the morning of February the 8th, 1969, falling over the Mexican state of Chihuahua. The meteorite airburst, breaking up in the atmosphere. An extensive search for pieces was then undertaken, and hundreds of specimens have been found, making Allende the most studied meteorite in history. Meteorites similar to Allende were previously known, but many were small and poorly studied. Scientists studying Allende identified a rare form of aluminum called aluminum-26, and they were able to use this as a clock to date the supernova which triggered the birth of the solar system. They found the supernova must have exploded less than 2 million years before the solar system first formed. Subsequent studies have found unusual isotopic ratios of krypton, xenon, nitrogen and other elements whose forms are also unknown in our solar system. The conclusion from many studies with similar findings is that there are a lot of substances in the pre-solar disk that were introduced as fine dust from nearby stars, as well as novas, supernovas and red giants. Close examination of the chondrules revealed tiny black markings up to 10 trillion per square centimetre, which were absent from the matrix and are being interpreted as evidence of radiation damage. Similar structures have turned up in lunar basalts, but interestingly not in their Earth-based equivalents, which would have been screened from cosmic radiation by the Earth's atmosphere and geomagnetic field. Therefore, it seems the irradiation of these chondrules happened after they had solidified, but before the cold accretion of matter took place during the early stages of the formation of the solar system when the parent meteorite body first came together. Scientists also discovered new forms of the elements calcium, barium and neodymium in the meteorite, which indicate that these elements came from a source outside the early clouds of gas and dust which formed our solar system. These specks persist to this day in meteorites like Allende and are known as pre-solar grains. This all supports the theory that shockwaves from a supernova either triggered the formation of, or at least contributed to the formation of our solar system. Now, a team of researchers, including Professor Alexander Hedger from Monash University, have decided to focus on one specific short-lived nuclei, beryllium-10, which was also present in the early solar system. Due to their short lifetimes, these nuclei could only have come from the triggering supernova. Their abundances in the early solar system have been inferred from their decay products found in meteorites. Many meteorites date back to the birth of our solar system, and as such, they're often considered to be a bit like builder's rubble left over from a construction site. They tell us what the solar system's made of, and in particular, what short-lived nuclei the triggering supernova produced. And that's interesting because different types of nuclei are produced by different supernova events generated by stars of different masses. And this is where Hedger and colleagues come in. They discovered that a supernova with about 12 times the mass of our Sun would have produced the sort of nuclei found in the meteorite samples they examined. Previous studies had focused on higher mass supernova triggers, which would have left behind a set of nuclear fingerprints that simply aren't present in the meteoric record. The authors reached their conclusions by examining beryllium-10, a short-lived nucleus containing 4 protons and 6 neutrons, and which is widely distributed in meteorites. In fact, the ubiquity of beryllium-10 was something of a mystery in and of itself. You see, many researchers had hypothesized that spallation by cosmic rays was probably responsible for the beryllium-10 found in meteorites. Spallation is a process where high-energy particles collide with an atom. In the process, they strip away protons or neutrons from the nucleus, resulting in the formation of a new nuclei. Now, these cosmic ray hypotheses all involve uncertain inputs, and they all presume that beryllium-10 can't be made in supernovae. However, by using new models of supernovae, the authors were able to show that beryllium-10 can be produced by neutrino spallation in supernovae of both low and high masses. Neutrinos are extremely weakly interacting subatomic elemental particles, which are commonly produced in supernova events, as well as in the core of stars and in nuclear reactions. The authors found that only a low-mass supernova triggering the formation of our solar system would be consistent with the overall meteoric record. You see, in addition to explaining the abundance of beryllium-10, this low-mass supernova model would also explain the short-lived nuclei calcium-41, palladium-107, as well as several other nuclei found in meteorites. The authors are now examining lithium-7 and boron-11 nuclei, which are produced along with beryllium-10 by neutrino spallation in supernovae. Hedger says identifying these fingerprints of the final supernova is what scientists needed to help them understand how the formation of our solar system was initiated.
Typically in the past, people have assumed that much of the beryllium-10 was made by cosmic ray spallation, and so there was a tension about making the right amount of beryllium-10. Supernova is the other possibility of making these, but if you make these, it would mean that at the same time you're also producing for your typical supernova of 15 solar mass star dying, that you're overproducing many of these other radioactive species that should have been present in the solar system as well. So what we have now done is some new calculation where we improved the calculations of production of beryllium in supernova and found if you go to a very low mass supernovae, so close to the minimum mass where supernova explode, in this case you would not produce many of these heavy elements that are mostly made by supernovas. You will make much fewer of those, but you can still produce the beryllium-10 in the supernova. You can actually make them quite efficiently there, and this way you avoid this tension in production between overproducing other things that normally is attributed to a supernovae.
How was the actual study carried out?
Our work is a theoretical work. So what we did is we did supernova simulations. So we did computer models of stars. We computed based on most updated nuclear physics. So we changed the code to include most recent nuclear physics update and nuclear reaction rates that hadn't been included in that form before in our calculations, and also adjusted them for most recent results in terms of energy of neutrinos, so these high energy particles inside supernovae that cause the spallation, and then carried out simulations of these supernova explosions. And the data that you compared to were taken from the literature.
You developed the model and you punched in the numbers, and the numbers matched with what was actually found in meteorites on the ground.
Yes.
Tell me about neutrino spallation. How does that work?
So, simple way of matching is you have these high energetic neutrinos. So when the star dies, the inner part, the iron core, so the star first burns through all of these different kinds of nuclear burning phases until it burns the last part of silicon into iron, and it builds up a heavier and heavier core of iron in the center. Eventually, this core of iron collapses, and when it does so, it collapses to a neutron star that becomes very, very hot, extremely hot, and so hot that it can produce tremendous amounts of neutrinos. In fact, it radiates away about 10 to 15% of the rest mass of this neutron star in form of neutrinos.
These neutrinos, they're not bothered by the other elements in the star, such as photons would be, so they move out very quickly. They leave the star.
Right.
We found that with Supernova 1987A, didn't we?
Yes, so it's true that neutrinos, typically, they can, at normal conditions that you have here on Earth, a neutrino can travel essentially unhindered for the most part. If you had a slab of lead between here and the next star, like Alpha Centauri, that could travel through that, most of them would get through this without being scattered even once. But when you go to a supernova in the early stages, they get so hot in the interior that they can actually trap the neutrinos, and so they only escape from the surface, and it shines for some time, for a couple of seconds.
When we think of neutrinos, we think of something that's very weakly interactive. I mean, the standard line is there are millions of them going through your thumb right now, or billions. But in the case of using neutrinos to knock bits off another atom, what is it, simply the sheer numbers of neutrinos?
Yes, it's the very large number of them and their high energy that allows them to do this. And the energy does change for neutrinos that arrive here from supernovae, but there's such a huge number that a tiny fraction of them will interact with nuclei. And in this case, they can knock out particles from the nucleus, different individual nucleons. So in practice, the neutrino hits a nucleus and deposits energy there, and then the nucleus goes in some excited state and it de-excites by emitting particles. And in this case, if you emit 2 protons, then we can get...
Yeah, you wind up with the beryllium.
We can get the beryllium-10.
Tell me about the importance of this research in understanding the origins of our solar system.
Well, it gives us the last concluding remarks. Okay, what really happened in this gas cloud? The solar system was formed, because the point is that we have so much more detailed information about composition by isotopes when we look at our own solar system compared to what we have from any other stars and the planets on them that we find. And because we have all of this isotopic evidence and fingerprints, it gives us a better idea, okay, how does it actually happen that any kind of solar system formed? What are typical triggers in these kind of gas clouds that eventually lead to transition? And we have, in this case, we have also some timing of what would happen from looking at all of these radioactive isotopes. I think this is very exciting. I mean, not all of these solar systems that form will do it in the same way, but there will be some variation. And in this case, we can point towards what was it that actually, how did this entire process come about for our own solar system? And I think this is kind of interesting if you want to know about our own origins and how did it all come about, our planets and where we are today.
The fact that this shows us the mass of the progenitor star, that's pretty impressive, isn't it?
Yes, that we can place the constraints. I mean, it's theoretical constraints that this comes from, but yeah, it shows us that our understanding of nuclear astrophysics gets increasingly more sophisticated and we can now really use this as a tool to understand what is going on.
That's Professor Alexander Hedger from Monash University. A giant rift valley, which may be evidence of buckling of planetary crust due to global contraction, has been discovered on Mercury. The massive feature, which is reported in the journal Geophysical Research Letters, dwarfs the Grand Canyon, being over 1,000 kilometres long, some 400 kilometres wide, and more than 3 kilometres in depth. The giant valley extends into a massive crater called the Rembrandt Basin, one of the largest and youngest impact basins on Mercury. Scientists discovered the valley using a new high-resolution topographic map of part of Mercury's southern hemisphere, created by stereo images from NASA's Mercury Surface Space Environment Geochemistry and Ranging spacecraft, MESSENGER. The study's lead author, Tom Waters from the Smithsonian National Air and Space Museum in Washington, D.C., says there are examples of lithospheric buckling on Earth involving both oceanic and continental plates, but this may be the first evidence of lithospheric buckling on Mercury. Unlike Earth's Great Rift Valley in East Africa, Mercury's Great Valley is not caused by the pulling apart of lithospheric plates due to plate tectonics. Instead, it's the result of the global contraction of a shrinking one-plate planet. See, the Earth has a crust and upper mantle, collectively known as the lithosphere, which is divided into many tectonic plates. However, Mercury's lithosphere consists of just one single solid plate that covers the entire planet. As Mercury cooled and contracted early in its history, say between 3 and 4 billion years ago, the planet's lithosphere buckled and folded, forming a complex series of valleys and rifts, much like the skin of a grape folds as it dries to become a raisin. Where the contraction forces are greatest, crustal rocks are thrust upwards, while at the same time an emerging valley floor sags downwards. The valley walls appear to be 2 large parallel fault scarps, step-like structures where one side of the faults moved vertically with respect to the other. Both scarps plunge deeply to the flat valley floor below. In fact, Mercury's contraction has caused the fault scarps bounding the Great Valley to become so large they've essentially become cliffs. The entire floor of this newly discovered valley is one giant piece of lithosphere that simply dropped between the two faults on either side. The elevation of the valley floor is far below the terrain surrounding the mountainous fault scarps. This suggests that the valley floor was lowered by the same mechanism which formed the scarps themselves. The best explanation for all this is that Mercury's interior cooled rapidly, forming a strong, thick lithosphere. It's all proof that Mercury's experienced a very different type of deformation compared to anything we've seen here on Earth. After a series of upgrades, the twin detectors of the Laser Interferometer Gravitational-wave Observatory LIGO are now back in operation to continue their hunt for ripples in the fabric of space-time known as gravitational waves. It was back on February the 11th, 2016 that LIGO scientists announced the historic first ever direct detection of gravitational waves. The waves were generated by the merging of two stellar mass black holes some 1.3 billion light-years away. The signal, named GW150914, was observed by LIGO's detectors in both Louisiana and Washington state on September the 14th, 2015. Then, on June the 15th, 2016, the LIGO collaboration announced the confirmation of a second gravitational wave detection, named GW151226, which had occurred on December the 26th, 2015, also from merging black holes. This event was even further away than the first, with an estimated distance of 1.4 billion light-years. And there was a third detection, but this is yet to be confirmed. It occurred on October the 12th, 2015. These initial detections were made during LIGO's first run after undergoing a series of major technical upgrades in a program called Advanced LIGO. That run lasted from September 2015 to January 2016, and since then engineers and scientists have been evaluating LIGO's performance and making a series of further improvements to its lasers, electronics and optics, which have resulted in further increases in sensitivity. Caltech's David Rexy, the executive director of the LIGO observatories, says this latest improvement in sensitivity, combined with a longer observing period during this run, is expected to result in further detections, thereby enhancing science's understanding of black hole dynamics. Astronomers believe that gravitational waves are generated by super-dense objects, like collisions between black holes and neutron stars. The increased sensitivity means LIGO should be able to detect black hole mergers at far greater distances than before, and therefore should be able to see more mergers than previously, and maybe also a few involving neutron stars. The LIGO detectors each comprise a high-powered laser, which is split into two beams which are then fired down two perpendicular 4-kilometre-long tunnels. They're reflected back at the end of the tunnel to special detectors. Any distortion in the return signal indicates the possibility of a gravitational wave passing through the observatory, and alternatively stretching and squeezing the very fabric of space-time in the process. The final Progress cargo ship flight for 2016 to the International Space Station has ended in failure, with the spacecraft crashing back to Earth. The Progress MS-04 65P cargo ship, carrying some 2,450 kilograms of supplies to the orbiting outpost, blasted off as normal aboard a Soyuz U-series rocket from the Baikonur Cosmodrome in the Central Asian Republic of Kazakhstan.
The ground propellant feed has now been terminated. Everything is on track. The auto sequence has been initiated. Standing by for the initiation of the engine start. The second umbilical has been retracted. We have main engine start. Engines coming up to turbo speed. All engines at flight speed. And liftoff. We have liftoff of the 65th Progress resupply vehicle, beginning a 2-day journey to the International Space Station. All engines performing nominally. A good roll, pitch, and yaw program reported from the blockhouse at Baikonur. Good control of the vehicle. Good vehicle stabilization reported. The Soyuz delivering 102 tons of thrust from its first stage engine, disappearing into a cloud bank. All vehicle parameters reported performing perfectly. 1 minute 15 seconds into the flight. Everything continues to perform nominally on the first stage performance of the Soyuz booster, with the Progress 65 cargo craft encased in the upper stage of the Soyuz.
The mission appeared to be going smoothly, with the 4 strap-on boosters and core stage all performing nominally. The liquid-fueled strap-on boosters were jettisoned as expected 1 minute and 58 seconds after launch, leaving the core stage's single RD-118 engine to power the launch vehicle for another 2 minutes and 47 seconds until its own liquid fuel supply was exhausted and it too was jettisoned.
We're coming up on booster separation and first stage shutdown, and we have confirmation of the separation of the first stage of the Soyuz booster right on time. The Soyuz booster and the Progress resupply vehicle, 30 miles in altitude, 73 miles downrange from the Baikonur Cosmodrome, traveling at 4,000 miles an hour. The second stage engine up and running in good shape. All parameters reported to be functioning normally, and we've had shroud jettison, so the Progress now exposed as it continues its trek uphill to its preliminary orbit. We're at the 3-minute mark into the flight. Good vehicle stabilization reported. The Soyuz booster tracking in perfect shape. Oil control system parameters are normal, reported by the blockhouse in Baikonur. And the second stage engine continues to fire in nominal fashion. The engine providing 96 tons of thrust as it continues to move right down the pike towards its preliminary orbit and spacecraft separation of the Progress resupply vehicle. We're coming up on stage engine shutdown and stage separation. Aft skirt separation and the stage engine up and running, providing about 30 tons of thrust to complete the Progress's climb to orbit. Will fire for just under 4 minutes to place the Progress into its preliminary orbit.
The Soyuz upper stage, which is hot-fired just prior to core stage separation, then continued the ascent, igniting its single RD-0110 engine, which should have propelled the stack for the remainder of the 8-minute 44-second ride to orbit.
Coming up on the 5.5-minute mark into the flight, no issues reported. Launch occurred on time at 8:51 and 52 seconds a.m. Central Time, 8:51 and 52 seconds p.m. at the launch site of the Baikonur Cosmodrome. 6 minutes into the flight, 2 minutes and 46 seconds of powered flight remaining. No issues reported. The roll, pitch, and yaw of the Soyuz booster and its associated Progress resupply craft all reported to be in nominal fashion. Flight controllers of the Russian Mission Control Center in Korolyov standing by to take over the rest of the flight of the Progress vehicle following stage shutdown and spacecraft separation.
However, mission managers at the Russian Federal Space Agency Roscosmos suddenly lost telemetry from the mission 6 minutes and 22 seconds into the flight.
This is Mission Control Houston. Telemetry was a bit ratty toward the end of the performance of the Soyuz booster, so we're standing by for confirmation from the Russian flight controllers that we indeed had a third stage shutdown and spacecraft separation of the Progress 65 cargo craft.
Although there were official reports that both the navigation and communications antennas had deployed, mission managers were unable to determine if upper stage separation had occurred or if the solar arrays had unfolded.
Telemetry being received at the Russian Mission Control Center in bits and pieces, indicating that the navigational antennas on the Progress have deployed. We're still standing by for confirmation that the solar arrays deployed. This is Mission Control Houston. The reports coming from the Russian Mission Control Center in Korolyov, indicating that the Progress 65 cargo craft, which launched at 8:51 and 52 seconds a.m. Central Time, that the Progress has been placed in a preliminary orbit. We're still trying to confirm through Russian ballistics exactly what that orbit is. We also have received confirmation that its navigational antennas did deploy, but we are still awaiting confirmation on the outcome of the solar array deployment activities. Apparently, the solar arrays, the telemetry being received at least, indicate that they are not stowed, but may not have necessarily deployed fully. So we are continuing to stand by on further updates from the Russian Mission Control Center. We're still analyzing telemetry that has been received from the Progress 65 cargo craft, which launched just 40 minutes ago from the Baikonur Cosmodrome in Kazakhstan. First and second stage performance of the three-stage Soyuz booster rocket was nominal. No issues reported. When third stage performance of the Soyuz booster began, and shortly thereafter, some ratty telemetry was noticed and reported by the Russian ballistics team at the Russian Mission Control Center. There were conflicting reports about the Progress 65's health at that point. What the state vector is of the Progress 65, its orbit in relation to the Earth. The International Space Station and its 6 crew members are flying over the northwest Pacific Ocean, just off the coast of Japan, in an orbit from northwest to southeast and at altitude of 252 statute miles. This launch was sending the Progress on a 2-day rendezvous to the International Space Station to arrive at the station on Saturday for a docking to the aft port of the Zvezda service module.
Then, within an hour of the launch, Roscosmos began receiving reports from Russia's Tuva region on the border with Mongolia of a large explosion and fireball in the sky, followed by reports of ground tremors and discovery of large pieces of rocket debris. Russia's TASS news agency later reported that a ground station did detect the break-up of the spacecraft shortly before it stopped transmitting telemetry data. A full investigation into the anomaly is now underway. Early indications are that the upper stage may well have shut down prematurely, preventing the Progress cargo ship from reaching orbit. It's the second time in 18 months that a Soyuz rocket carrying a Progress cargo ship has crashed and burned. Back in 2015, the Progress M27M cargo ship tumbled out of control in low orbit for 2 weeks before re-entering the atmosphere and crashing back to Earth. That failure was eventually traced back to the interface between the Progress and the Soyuz upper stage. And back in 2011, the Progress M12M cargo ship also crashed back to Earth in eastern Russia shortly after launch, following what turned out to be a blocked fuel line in the Soyuz upper stage. The Progress MS-04 was the fourth of the new improved Progress MS series of spacecraft, which are equipped with new computer, navigation and communication systems now being rolled out on both Progress cargo ships and Soyuz manned capsules. The Progress was carrying over 700 kilograms of propellant, which was to be pumped into the Russian Zvezda module's fuel tanks. It was also carrying 420 kilograms of fresh water, more than 50 kilograms of oxygen, 315 kilograms of food, and 115 kilograms of medical and personal hygiene supplies. The cargo ship was also carrying a new upgraded Russian Orlan spacesuit, an experimental Russian water recycling unit, new equipment for the space station's air purification system, as well as new cables, photographic equipment, and new scientific experiments. All these supplies would have kept the space station's 6-person crew stocked up until May. As it now stands, the orbiting outpost supplies should last until March. However, Japan is about to launch another HDV cargo ship to the space station aboard an H-2A rocket in the next few days. And SpaceX is slated to launch a Dragon cargo ship next month. Another Progress is due to fly to the ISS in February, and that should be followed in March by Orbital's next Cygnus cargo ship. And that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, and from SpaceTimeWithStuartGary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C.
This is SpaceTime with Stuart Gary. For more, you can follow us on Facebook, Twitter, and Tumblr. Just search for SpaceTime with Stuart Gary.